Hello, and in part 2 of these talks about equivalent networks, we'll be looking at Thevenin's theorem. Thevenin's theorem is one of those things that you're often asked to quote in exams, so it's a good idea to memorize the key points of what it says. So, Thevenin's theorem says this: any two-terminal linear network can be replaced by an equivalent network composed of a voltage source and a series resistor with no effect on any external circuit. Key points here is that the network that you're replacing has got to be linear. So the voltages and the currents at every point in the network have got to be related to the independent sources by a linear expression of the form output is the sum over all of the inputs times a set of constant factors. And as long as that is true, we can create an equivalent network which results in the same current flowing and the same voltages across the terminals A and B, the equivalent network containing a single voltage source and a single resistance. I can show you an example. Here we have a network. It consists of two resistors, a voltage source and a current source. It is currently outputting a current of 2.143 milliamps, and there's a voltage across its terminals of 2.143 volts, with a 1K resistor at that point there. And here is the equivalent network. A single voltage source with a single resistance in series. As you'll see, it's outputting the same current and the same voltage. And this is true no matter what is connected to the terminals. I could reduce this to a 10 ohm resistor, and this one to a 10 ohm resistor, and once again the voltages and the currents are identical. These components that you attach to the equivalent networks don't have to be linear components. I could replace this with a diode. Let's take a light-emitting diode because they're more fun, and connect a light-emitting diode across this terminal. That amount of current and that amount of voltage will flow. Do exactly the same thing with the other circuit, with the equivalent network, and it behaves in exactly the same way. And I could put anything between the two terminals of this network, and I would get the same current and the same voltages. And provided the conditions are met, that this is a linear network, then I can always find an equivalent network which behaves in the same way. And that's what Thevenin's theorem says. Quick reminder, because it's important, if you're asked to quote Thevenin's theorem, always remember that it's for two-terminal networks. The networks have to be linear, and the equivalent circuit is composed of a voltage source and resistor in series. Those three things have to be present in order to get a correct statement of Thevenin's theorem. Two-terminal, linear, voltage source and series resistor. Okay, this is a comparatively short one. Next time we'll be looking at the problem, how do you work out the voltage source and the series resistance in order to produce a Thevenin equivalent network?